We will begin Unit 5 of the course with a discussion on Newton's law of gravitation. Now the question, what is it that holds everything in the universe together? What is it that holds the solar system together? What makes the earth goes around the sun? What makes an object that is thrown up to come back? You see, all these are intriguing scientific questions. But for many of us, something that is thrown up is supposed to come back. Well, there is a big difference between answering a scientific question and taking something for granted. It took the genius of Newton to figure out that if an apple falling from a tree falls towards the earth, there must be something that is holding everything on the surface of the earth where it is supposed to be. Well, if the earth is spinning very fast, if there is no force holding objects to the earth, they will all fly away. So what did Newton say? Newton came up with this fantastic law which says every object attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the distance between their centers. The greater the masses, the greater will be the attraction between the two objects. The greater is the distance between the objects, lesser will be that force. Can you represent this as a mathematical statement? The force between two objects is directly proportional to the product of their masses and inversely proportional to the distance between their centers. Here I have a mass m1, another mass m2, separated by a distance r. Now we can rewrite this law using mathematical notation. It will be F is directly proportional to m1, m2 divided by r squared. This is the statement of Newton's law of gravitation. Well, that statement can now be rewritten by replacing the proportionality sign by an equal sign, adding a constant. We have been doing that right through the course. What does this stand for? The uppercase G is the constant of proportionality, and it is called the universal gravitational constant. In other words, this G has the same value everywhere in the universe. It doesn't change. The value of G is the same for the force between Earth and the Sun. It is the same for the force between Earth and the Moon. It is the same for the force between one galaxy and the other. It is the same for the force, the gravitational force between any object anywhere in the universe. Now, can you tell me what is the unit for measuring G? To figure out the unit, what all you need to do is solve for G. Look at this, I'm going to solve for G. G equal to F multiplied by R squared divided by m1 times m2. And so what will be the unit of G? It will be Newton meter squared per kilogram squared. That's right. So G has a value, it has been measured. G has been measured very accurately. It has a value 6.67 times 10 to the power of negative 11 Newton per meter squared per kilogram squared. Alright, I have given you some scenarios here. Now I want you to watch this. Very important concept. You have a mass m another mass m, two equal masses separated by a distance d, and the force between them is F. If you double one of the masses, keeping the distance the same, the force will double. Is that right? Because F equal to G m1 m2 over r squared. If you double both the masses, the force will become 4 times. Why? Because it is now 2m times 2m divided by d squared. So the 2 times 2 will make it 4 times the original force. If the first mass remains m and the second mass is now 3 times the original mass, the force between them will be 3F, where F is the force between m and m. Alright, now let's see what happens if you change the distance between them. Well, as the distance decreases, the force will increase. Now the question is, by how much? Alright, the force between a mass m and another mass m separated by a distance d is 1F. What happens if you increase the distance to 2d? The distance is doubled. Now remember, in the formula for F, d is squared on the denominator. That means when the distance is doubled, the force will become 1/4 of the original force. So the new force now is 1/4 of the original force. On the other hand, if the distance is halved, from d the distance is made half d, what will happen? The force will become 4F. I want you to write down those expressions and check these out. Now look at this interesting scenario. You double the first mass, double the second mass, and double the distance, the force will remain the same. You want to check it out on the equation? Alright, I would like you to do that. But these are very interesting and important concepts. Okay, let's now revisit the idea of weight of an object. What is the definition of weight that we have discussed earlier? Weight of an object is the force with which an object is being pulled towards the center of the earth. The weight of an object is the gravitational force that object experiences due to the pull of the earth. Is that right? Yes, it is. Now, what is the gravitational force on this ball by the earth? What is the force with which the earth pulls this ball? I have written that equation here. If the mass of the earth I write as m sub e, and the mass of the basketball is m sub b, and the radius of the earth is r sub e, then the force exerted by the earth on this ball is F equal to G m e m b divided by r e squared, where we will assume that the distance between this ball and the center of the earth is the radius of the earth. Is it okay, that assumption? That's correct. Well, and this force is what we call the weight of this basketball. So weight of an object is the gravitational force the object experiences due to the pull of the earth. Okay. And therefore, we will now be able to obtain an equation for the weight of the earth. Weight of an object on the surface of the earth is a measure of the gravitational force on it by the earth. Now, here I have the earth, and here is an object of mass m. If the mass of the earth is represented by m sub e, and its radius is r sub e. Alright, the radius of the earth is r sub e. the mass of the Earth is m sub e, the gravitational force on an object of mass m on the surface of the Earth can be written as Fg. What does Fg stands for? Gravitational force on this object is g times me times m over re squared. We will use these notation right through the course. The uppercase m sub e is the mass of the Earth, r sub e is the radius of the Earth, and lowercase m is the mass of the object. Well, F sub g is the weight of the object. Now, what is the weight of the object that we have been using to measure? What is the weight of this object? Normally, how do we measure it? It is the mass of the object multiplied by the acceleration due to gravity. Is that right? Yes. So weight equal to mg, where g is the acceleration due to gravity. So we can actually replace this F sub g by this mg. Let's do that. We have therefore mg equal to g times mem over re squared. And you notice that the lowercase m, the mass of the object, appears on either side, which will cancel. And what does that give you? That gives us an equation for g, lowercase g, the acceleration due to gravity. The equation for the acceleration due to gravity is uppercase g times me over re squared. That means that the value of acceleration due to gravity is not a constant. It depends on the radius of the Earth. So if I take this object away from the surface of the Earth, the distance is going to increase. That means the value of g is going to decrease. Now tell me, is the value of g the same everywhere on the surface of the Earth? Well, no. Why not? Because the Earth is not a perfect sphere having the same radius all over. If you look at the picture of the Earth is actually like an orange. It is bulging at the equator and slightly flat at the poles. That means the equatorial radius, this RE, is greater at the equator and smaller at the poles. So where do you have maximum value for acceleration due to gravity? The value for acceleration due to gravity is maximum at the poles, where the radius of the Earth is the least. And the value of g is the least at the equator, where the value of the radius of the Earth is maximum. And if you now go higher and higher away from the Earth, the value of g will decrease. That's right. Okay, now this can now be written as cross multiply GRE squared equal to big G times MV. Big G times ME equal to GRE squared. Alright, don't confuse between the big G and the small g. The big G is a constant, it doesn't change no matter where you are. But the small g is the acceleration due to gravity, which actually varies, looking at that equation. Now, the significance of this statement is that there are many places in this lesson where we may need the value of big G multiplied by ME, the mass of the Earth times the universal gravitational constant. Now, these values are not very readily available for most of you unless you remember them. But look at this, GRE squared, where the G is the value of acceleration due to gravity on the surface of the Earth, which we can take as 9.8. Although it doesn't remain a constant, we can take an average value of small g as 9.8 meter per second squared. And RA is the radius of the Earth, which everybody must have a fair idea what it is. So an average value of g on the surface of the Earth can be obtained by using the known values of mass of the Earth and the radius of the Earth. You can actually do that. The mass of the Earth is 5.98 times 10 to the 24 kilogram. And the radius of the Earth, I would like you to remember this value, 6.38 times 10 to the 6 meter. That is the radius of the Earth. But the average value, we know the radius slightly differs at the equator and at the poles. This is an average value. And using these two values, we can calculate a value for acceleration due to gravity. The value of the universal gravitational constant is 6.67 times 10 to the negative 11. What's the unit there? Newton meter squared per kilogram squared. And this is the mass of the Earth, and this is the average radius of the Earth, and that gives you our famous value 9.8 meter per second squared. So this is the average value of acceleration due to gravity on the surface of the Earth. So this g can be replaced by 9.8 meter per second squared. The radius of the Earth is 6.38 times 10 to the 6. So wherever we need big G times the mass of the Earth, we can replace that by small g times RE squared. I will ask you that a little later, so don't forget that. What happens to the value of g as you go higher and higher? The value of g at an altitude h. The value of g will change as the object is taken away from the surface of the Earth. At an altitude h, when the object is at an altitude h, the distance between the object and the center of the Earth will be RE plus h. Is that right? So we will replace the radius of the Earth now with the radius plus the altitude. So the value of g at an altitude h will be the universal gravitational constant times mass of the Earth divided by RE plus h all squared. Let's find the value of g, the acceleration due to gravity, at a height 200 kilometers from the surface of the Earth. Well, we know the mass of the Earth from the previous problem. We know the radius of the Earth. H is now given as 200 kilometers, and we know the value of the gravitational constant. Let's put all those things there. 6.67 times 10 to the negative 11 times mass of the Earth divided by radius of the Earth plus the altitude at 200 kilometers is 0.2 times 10 to the 6 meters. Alright, can you use your calculator to work out what this is? That will give you 9.2 meter per second squared. So if you go to a height of 200 kilometer, the value of acceleration due to gravity will decrease to 9.2 meter per second squared. That means the weight of the object will be less at that altitude. Is that right? That's correct. Let's now talk about gravitational field. What is a field? Now, this is a concept we will talk about again in physics too. Whenever we talk about a force, we use the concept of a field to describe it. Now, suppose an African chief says, what you see within this fence is my field. What does that mean? That is my field. What he means is, this is where I exert my authority. Now, you can use the same meaning to describe a gravitational field. Earth has a gravitational field. In other words, the space surrounding the Earth, where the Earth will exert a force on other objects, is the gravitational field of the Earth. So, gravitational field of an object is a three-dimensional space around that object, where that object will exert force on other objects. That is the definition of a force field. The statement of the law of gravitation implies that an object placed outside the Earth's surface will experience a force towards the Earth. Now, this is true no matter where the object is placed. No matter where the object is placed, if the object is on the surface of the Earth, it will experience a force towards the Earth. If the object is taken to an altitude h, it will experience a force towards the Earth. No matter where you place the object, it will experience a force towards the Earth. That means the three-dimensional space surrounding the Earth, where it will exert a force on other objects, is the gravitational field of the Earth. This is equivalent to saying that there is a gravitational force field around the Earth. Now, here is the Earth. I have used arrows to represent this. If I keep an object here, it will fall towards the Earth. If I keep an object here, it will fall towards the Earth. If I keep an object over here, it will fall towards the Earth. That means the space surrounding the Earth, where the Earth exerts a force on other objects, is the gravitational field of the Earth. Now, why have I used the arrows pointing towards the Earth to represent that field? I have used arrows to show that the direction of that force is directed towards the Earth. That means the field is a vector quantity. The field has a magnitude and a direction. What is the magnitude? Magnitude is the amount of force an object will experience, and the direction is towards the Earth. You see, a field is a vector. It has a magnitude and a direction. All right. The gravitational force field is a vector quantity that has a magnitude and direction. The direction is towards the center of the Earth, as is indicated by these arrows. The magnitude or strength of the force field. How do you know what the strength of the force field? Now, where is the strength of the field greater? If you look at these lines that represent the force field, where are they closer together? Now look at my marker moving. Now, along this circle, the lines that represent the field are closer together than along this circle. That means the strength of the field is stronger. The field is stronger closer to the Earth than when you go far away. The strength of the field is greater at points that are close to the surface of the Earth. If you move away from the surface of the Earth, the strength of the force field will become weaker. So the distance between these field lines, these lines can be called field lines. The distance between the field lines indicates how strong or how weak the force field is? Well, there is a definition for the strength or the magnitude of the gravitational field at a point. It's a standard definition. Now I want you to learn this. The strength of the gravitational force field at a point is defined as the force per unit mass placed at that point. So if I have a mass of 1 kilogram, suppose this ball has a mass of 1 kilogram, it has approximately 1 kilogram. If I can now measure the force on this basketball placed at this point, that will be a measure of the strength of the gravitational field at this point. If I take this basketball to an altitude of 1 kilometer and measure the force on this 1 kilogram, that will be a measure of the gravitational force at that point. So in order to measure the strength of the gravitational force at a given point, you place a unit mass of 1 kilogram and measure the force it experiences, and that will be a measure of the gravitational force. The strength of the gravitational field at a point is defined as the force per unit mass placed at that point. What is the unit for gravitational field? It is force per unit mass, Newton per meter. Let's write that down and see what that is. The unit of the gravitational field is Newton per meter. Now, do you know what a Newton is? A Newton is a kilogram meter per second squared. Is that right? Alright, now let me make one correction what I have been saying, which is the strength of the gravitational field is the force per unit mass. Force per unit mass. What is the unit for that? Newton per kilogram, not Newton per meter, as I said earlier. So make that correction, please. The strength of the gravitational field is force per unit mass. It must be Newton per kilogram. So it must be Newton per kilogram. And if you remember what a Newton is kilogram meter per second squared. And if you divide that by kilogram, you notice kilogram and kilogram will cancel. That gives you the unit of the gravitational field is a meter per second squared. The unit of gravitational field is meter per second squared. But aren't you familiar with another quantity that is measured in meter per second squared? Acceleration. Yes. So let's see how this is related. The force experienced by a unit mass placed at a height h above the surface of the earth. Can you write down that equation? What is the equation for the force experienced by a unit mass placed at a height h above the surface of the earth? Well, this is the equation for the force experienced by an object placed on the surface of the earth where h is 0. We say the force of gravity on a mass of 1 kilogram. Now, if you remember, this is our original equation. If you place an object on the surface of the earth, the force of gravity on it will be F equal to g times mass of the earth times mass of the object divided by the square of the radius. So remember, we are not placing the object at a height h, we are placing the object on the surface of the earth, where the distance between the center of the earth and the object is the radius? Well, since gravitational field is the force per unit mass, then what is the value of this m? That will be 1. When this m equal to 1, you can see the force per unit mass is gme over re squared. And this is a measure of the gravitational force on the surface of the earth. If you now want to find the gravitational field at an altitude h, replace this Re by Re plus h. Is that right? Yes. So the force field at a distance h will then be gme over Re plus h all squared. So if this is the gravitational field on the surface of the earth, this quantity where m equal to 1, then this will represent the gravitational field at a height h above the surface. Alright, and this is equal to g, is that right? Because gme over Re squared is what is called acceleration due to gravity. And therefore, this is a very interesting phenomenon. The gravitational field at a point is simply a measure of the acceleration due to gravity at that point. You see how the unit is now meter per second squared agrees with this definition? So the gravitational field at a point is a measure of the acceleration due to gravity at that point. Now, gravitational field can be represented by vector notation as Fg equal to negative Gj. Now, did you understand this? Gravitational field is a vector that is directed towards the earth. Anything that is directed downward is a y vector. Anything that is directed in the vertical direction is a y vector. And since the gravitational field is directed towards the earth, it is directed downwards, it is a negative vector. The gravitational field is a measure of g at any point. And you can see as we move away from the earth, the value of g will become smaller and smaller. That means the magnitude of this vector will become smaller. Where is the magnitude of this vector the greatest? The magnitude of this vector is the greatest at the surface of the earth. So look at the vectors that I have drawn at various points. If you want to draw the gravitational field vector here, it is this arrow, negative g. Whereas the gravitational field at a point nearer to the surface of the earth is represented by a longer arrow. The length of the arrow represents the magnitude of the field. So as you go away, the length of the arrow becomes smaller and smaller, indicating that the value of g is becoming smaller and smaller. The gravitational force field becoming weaker and weaker as we go away from the surface of the earth. Now, will there be a point where the gravitational force field due to the earth is absolutely zero? Well, for practical purposes we can say the gravitational force field at infinity, at an infinite distance from the earth will be zero. Alright, so the unit of gravitational field is, we talked about it, it is Newton per kilogram, which is the same as meter per second squared. Okay, let's do a small problem. What is the gravitational field at a point where the weight of an object is 3 kilograms? the weight of a 3 kilogram object is negative 15 Newton J. Now, if you understood the concept I described, you can give me the answer right away. Gravitational field is the force per unit mass. Now, the weight of a 3 kilogram object is negative 15 Newton, means that is the force on the 3 kilogram there. Therefore, if you place 1 kilogram, what will be the force? If this is the force experienced by the 3 kilogram object, what will be the force experienced by 1 kilogram object? Gravitational field at a point is force per unit mass. Therefore, the gravitational field at that particular point will be the force divided by the mass, force per unit mass. That will be negative 5 Newton per kilogram J. That will be negative 5 meter per second squared J. Is that right? It's at a very far distance from the Earth. Let's now talk about orbital speed of a satellite. What is the meaning of orbital speed? If I can throw this basketball with sufficient velocity, you know, if I throw this, the basketball will begin to fall. Is that right? Now, if I throw it with sufficient velocity such that as the ball begins to fall, the surface of the Earth falls exactly the same amount. Let me see if I can show that to you in a drawing here. Now, this is our Earth. If I throw this basketball with the velocity so that when the basketball falls, you see that as it goes, it is going to fall like this. And you can see here, the basketball has fallen by that amount. And the surface of the Earth at that point also has fallen by the same amount. So, if you can throw this ball with such a speed that the amount of fall of the ball equal to the amount of fall of the surface of the Earth due to the curvature of the Earth, then this ball will never come back to the Earth. It will keep going round and round. In fact, that is what our moon does. The moon is continuously falling towards the Earth. But because it has sufficient speed, the amount of fall of the moon equal to the amount of fall of the surface of the Earth. And therefore, the moon goes round the Earth in an orbit. Now, the question we are trying to answer here is, what is the minimum speed we require so that an object thrown will simply go in an orbit around the Earth? Okay, an object thrown with sufficient speed can be made to go around the Earth in an orbit. You can see here, if this cannon is fired with a low velocity, the ball will come back. But at a particular velocity, the fall of the ball and the fall of the Earth will be the same, and with that velocity the ball will keep going in an orbit. So the speed needed to keep a satellite in orbit around the Earth is called its orbital speed. And you know how important these concepts are for space travel. Now consider a satellite of mass m placed in an orbit h meter above the surface of the Earth. The distance of the satellite from the Earth will be radius of the Earth plus h. That's no problem there. When the satellite is in a low orbit, we're going to make an approximation here. this h will be very small compared to the radius of the Earth, and therefore we are now going to say the distance of that satellite from the center of the Earth will be RE. That means when the satellite is placed at a low orbit, not very far from the Earth, the distance of the satellite from the center of the Earth is RE plus h, can be approximated as RE, because compared to the radius of the Earth, the altitude of that satellite is very small. Therefore, we can write an equation now. If m is the mass of the satellite and me is the mass of the Earth, the force of gravity on this satellite can be written as, alright, can you write that equation? What is the force of gravity? Force of gravity is G MEM over RE squared. Well, if you want to make this object to go in a circle, what is the force that keeps an object going round in a circle? The force that keeps an object going round in a circle is called the centripetal force. Do you remember the equation for centripetal force? Centripetal force is mv squared over r, where v is the tangential velocity, or that is what we call the orbital speed. Alright. Now, it is this force that provides this centripetal force for the satellite to stay in the orbit. So, it is the gravitational force on the satellite that provides the centripetal force that keeps it in the orbit. If v is the speed of the satellite in that orbit, then that centripetal force will be mv squared over re, where re is the radius of the Earth. That means we can now take this quantity, the gravitational force on the satellite, and set it equal to the centripetal force, because this centripetal force is provided by this gravitational force. Let's equate those two equations. mv squared over re equal to g MEM over re squared. Now I have used different colors here. First of all, green colors, m and m will cancel from either side. And do you remember, I told you I will ask you, we said GME can be replaced by a more familiar quantity. What is GME equal to? Will be small g times RE squared. Let's do that. When you do that, I'm going to do that over here. Watch me do that. I'm going to cancel the m and the m and replace the GME by GRE squared. And you can see, now what happened there? If GME is GRE squared, you can now have V squared over RE equal to GRE squared over RE squared. And multiplying by RE, I can make that RE cube, and RE squared on the denominator will cancel with the RE cube, leaving a GRE. So what you see here is solving that equation gives you V squared equal to GRE, where V is the orbital speed. And therefore, what is V equal to? V equal to square root of GRE. The orbital speed, the speed that is necessary to keep an object in a low orbit. I'm not talking about a high orbit. In a low orbit is square root of GRE. We know the value of G on the surface of the Earth. We know the radius of the Earth. Therefore, we can calculate the orbital speed. calculate the tangential velocity required to keep a satellite in a low orbit around the Earth. You see, look at that low orbit. Low orbit means you can use the radius of the Earth as the distance. Well, we just obtained that equation. V orbital equal to square root of GRE, and that is square root of 9.8 times 6.38 times 10 to the 6. That's the radius of the Earth. And that is 7.9 times 10 to the 3 meter per second, which is 7.9 kilometers. So, if I can throw this ball with a speed such that in 1 second it will cover about 8 kilometers. In 1 second, if this can cover 8 kilometers, that means at that time the amount of fall of the ball will be equal to the amount of fall of the surface of the Earth. The ball will go around in that low orbit. And that is the meaning of orbital velocity. Let us now spend some time talking about the potential energy of a two-body system. What is the meaning of a two-body system? If I have now my basketball, this basketball and the Earth form a two-body system. And you know that if I lift the basketball to a height, the work I did will increase the potential energy. Is that right? So tell me, when do two objects have minimum potential energy? When this ball is on the surface of the Earth, the potential energy of the ball-Earth system is the minimum. And if I move this ball away, I am increasing the potential energy of the Earth ball system. So, in this lesson, we're going to say the potential energy of the Earth object system is zero at infinity. Now, is that a contradiction? If the potential energy is zero at infinity, isn't that the maximum value? Because the potential energy is maximum at very large distance. When the distance between the object is very large, the potential energy should be very large. Well, we will consider that very large value will be zero. That means as you come closer and closer to the Earth, the potential energy becomes negative. And I'm going to give you an equation which we will be using in this lesson for calculation. What is the equation for the potential energy of an object placed on the surface of the Earth? I'm going to say the potential energy of an object placed on the surface of the Earth. You know potential energy is represented by U. So, potential energy of an object placed on the surface of the Earth is negative big G times ME times M divided by RE. Now, this is the equation for the potential energy. The potential energy is negative on the surface of the Earth. It has the least value on the surface of the Earth. If you now go higher and higher, this RE will be replaced by RE plus H. So what is the potential energy of an object? What is the potential energy of an object at an altitude H? It will be negative G times MEM over RE plus H. Well, tell me, which of these values is greater? Well, this is greater. Now, you notice that when RE plus H is greater than RE. When the denominator is greater, the value of the quantity will be smaller. right? And a smaller negative means it is increasing. So as h increases, the potential energy increases, and the potential energy is 0 at infinity. Now this is the same as saying that we are at the bottom of a potential well. You see that? We are all trapped under the bottom of a potential well. If this is the surface of the earth, we are all in this well here. You see that? I am in the potential well, and I have the potential energy given by this equation, negative G MEM over RE plus H. Now how can I escape this well? Here, this is me here. How can I escape this potential well? If I jump up, well, I will come back. It's like a frog trying to jump out of a well. Have you tried? Have you seen that? The frog will try its best to come out, but each time it jumps, it goes back. Now, if I can muster up enough energy, I can have a big jump so that I escape the potential well. What will be my potential energy when I escape the potential well? Well, my potential energy will be 0. That is the maximum potential energy. When I jump out of the potential well, my potential energy will be 0. In other words, the speed I must have, what kind of speed should I have, with what kind of velocity should I jump out of the well so that I come out of that well? That speed is called the escape speed. What is the speed you need so that an object escapes completely the gravitational field of the earth? Its potential energy becomes 0. Well, we will be using these equations in our calculations, so keep track of this. The potential energy of an object on the surface of the earth is negative G MEM over RE, and potential energy at an altitude h will be negative G MEM over RE plus H. Be replaced by G RE squared. And therefore, U surface can now be written as negative GRE squared. The GRE squared is the replacement of big G ME. And now, this RE and 1 RE from the numerator cancels, that giving us negative small g REM. This is a very good equation. The potential energy of an object placed on the surface of the earth. And now, potential energy of a mass m at an altitude h will be negative G MEM over RE plus H. So don't mix up these two equations. And that will be negative, this GME can be replaced by GRE squared. So that will be negative GRE squared M over RE plus H. This is the potential energy of an object of mass m at an altitude h. This is the potential energy of an object of mass m on the surface of the earth. Let's now talk about escape velocity. We are now in a position to talk about it. Escape velocity. Escape velocity is the velocity that you need to give to an object so that the object escapes the potential well. Alright, let's figure it out. Escape velocity, V escape, is the minimum velocity of projection so that the object will escape the Earth's gravitational field entirely. In other words, its potential energy will become 0. That's the meaning there. Since we have chosen potential energy at infinity to be 0, the potential energy of an object of mass m on the surface of the earth we know is this. This is the potential energy of an object on the surface of the earth. The potential energy of the same object at infinity will be 0. Suppose V escape is the velocity of projection. If you project an object with that velocity so that the object escapes the Earth's gravitational field, then this velocity V escape is just enough to take the object out of the potential well. So you give the object that velocity, the object just comes out of the well and collapses. That means its velocity will be reduced to 0. This velocity is just enough for it to escape the potential well. Okay, we will now use the conservation of energy to obtain an equation for the V escape. What is the conservation of energy? The total potential energy and kinetic energy on the surface of the earth must be equal to the total potential energy and kinetic energy at infinity. Alright, so U surface plus K surface equal to U infinity plus K infinity. The sum of the potential and kinetic energies of an object on the surface of the earth must be equal to the sum of the potential and kinetic energies of the object at infinity. Well, we have all these values. On the surface of the earth, the potential energy of the object is negative g-ReM. And if you throw the object with a velocity v escape, its kinetic energy, the moment you project it, will be 1/2 mv escape squared. When the object reaches infinite distance from the earth, its potential energy will be 0. Its kinetic energy also will be 0 because the velocity is just enough for it to reach infinity. That means its total energy on the surface of the earth will be negative g-ReM plus 1/2 mv escape squared. This is the total energy on the surface of the earth. And total energy at infinity equal to 0. So we will now take this quantity and set it equal to 0 and solve for V escape. A neat way to get an equation for the escape velocity. So we have negative g-ReM plus 1/2 mv escape squared equal to 0. And that means multiply by 2 and divide by m. M will cancel. Multiply by 2, negative 2g-Re plus V escape squared equal to 0. Or V escape squared equal to 2g-Re. Or V escape is square root of 2g-Re. Well, we will now use these equations and all the concepts we developed so far in solving problems. Alright, I'm going to do that as a second part. So I'm going to stop this part here and I will solve problems for you using these concepts. Also, we will discuss Kepler's planetary laws in the second part. Alright, I'll see you for that in a little while.